If you've ever been swimming in the ocean, you know that a good chunk of that experience is being force-fed gallons of salt water. You come out feeling like a crusty, oversalted fish, and you're desperate for a sip of good, clean, fresh water. Well, multiply that experience by 10, and you get one of the saltiest bodies of water on Earth. Utah's Great Salt Lake. It's so salty, they had to change its name. It's so salty, it forms crystals. It's so salty that half of it turned purple. In fact, until the 1800s, people thought the only way to explain the salt was a secret underground tunnel connecting it to the Pacific Ocean. Today, that idea doesn't hold water, but the actual story is almost as strange. See, 30,000 years ago, the Great Salt Lake took up a quarter of Utah and was full of fresh water. But then it went through a dramatic transformation. We know this in large part because of a pioneering scientist who had a little help from some very, very small friends. In the 1930s, Ruth Patrick set off into the water of the Great Salt Lake. She carried a long pole with a pointed metal tube on the end, which she plunged deep into the muddy peat at the bottom of the lake. When she pulled it back up, the tube was filled with a sample of bluish-gray mud. Inside of this mud were the treasures she was after. Patrick was collecting the remnants of tiny single-celled algae called diatoms. These otherworldly-looking little guys have a hard silica cell wall called a frustule that you can only truly appreciate under a microscope. She was collecting them because the hard silica of diatom frustules preserves really well in sediments at the bottoms of lakes and oceans. Yes, they can live in both fresh and salt water, but every species of diatom has a specific saltiness level that they're usually found in. And Patrick knew that she could use them to prove that tens of thousands of years ago the Great Salt Lake was full of fresh water. While most of her samples alternated between fresh and salty diatom species, the deepest and oldest samples had almost all freshwater diatoms. So that was like a totally different lake. In fact, back when those diatoms were alive, the Great Salt Lake was called Lake Bonneville, and it was nearly as big as Lake Michigan. But around 15,000 years ago, so not that long ago, a wall of the lake eroded and collapsed, leading to what scientists think was one of the biggest floods in Earth's history. 241 Olympic-sized swimming pools drained from the lake every second. That might sound too big to be true, but the evidence is everywhere. Over time, layers of mud and sediment accumulated at the bottom of the lake. When researchers drilled down through these layers, they found one where the sediment suddenly changed color as more carbonate minerals appeared. They think that abrupt change was the moment of the flood. And you could still see where all the water went. It carved a path through Red Rock Pass and the Snake River Plain in Idaho. Afterwards, more water evaporated during a series of droughts, and the lake shrank even more. In fact, scientists can see this decline by looking at which sediments contain diatoms that live in deep, dark water. Those diatoms tell us that as the water level declined, light penetrated through more of the lake, and this habitat was lost. By around 13,000 years ago, the lake became something similar to what we see today. 10 meters at its deepest point, a lot less than the 300 meters Lake Bonneville reached. And as the water in the lake went down, the salt concentration went up. See, the Great Salt Lake has 3 rivers flowing into it, all of them always carrying a little bit of salt, and then no rivers flowing out. So a lot of that water evaporates, but the salt can't evaporate, so it just sits there, accumulating. And the concentration of salt in the north half of the lake has gotten a whole lot higher, thanks to, if you could believe it, us humans. But before I tell you about that, a quick word from our sponsors. Thanks to Jump for supporting this SciShow video. Jump is a statistical analysis software designed to help you with powerful analytics. If you're working with a giant data set that has what feels like millions of variables, you could use Jump's predictor screening functionality to highlight the most meaningful variables and avoid wasting time and resources on the other variables. With Jump, you can also use multivariate approaches like principal components analysis and partial least square regression to untangle which of those variables hold the most leverage. And you don't have to stop there. The Advanced Modeling and Statistics Suite in Jump means researchers can use the software from the variable screening stage all the way through data analysis. They offer all of that with a 30-day free trial for anyone, anywhere at jmp.com/scishow. In 1902, the Southern Pacific Railroad Company wanted to cut down the time that it took to send trains all the way around the lake, so they built a 19-kilometer wooden trestle bridge right across it. But by the 1940s, the wood trestle needed repairs and upgrades to support heavier trains. Hoping for a more robust solution, the railway company built a solid rock-fill causeway in 1959, but unlike the wood beams that made up the trestle, the piled-up rocks mostly stopped water from flowing through them. So from that point on, the Great Salt Lake was split into two halves, the north and the south. Since the railroad company was in the business of efficient travel and not studying waterway dynamics, they created a lake where the rivers pretty much only flowed into the south half, leaving a stagnant north half. Over time, salt levels built up even more in the north, reaching 10 times higher than the average ocean. So today, pretty much the only thing that can live there are microorganisms called haloarchaea, which can survive in high salt concentrations. And that shift in lake dwellers was pretty easy to see because haloarchaea make a purple-colored protein that turned the top half of the lake a totally different color than the bottom half. In fact, the lake is now so salty that the diatoms, which told us so much about its past, can barely survive. You can only find them living near the freshwater rivers that flow into the lake. Even the southern half of the lake is still 4 times saltier than the average ocean, and that has some unappealing consequences. When organic material gets trapped under dense, salty water at the bottom of the lake, bacteria that thrive without oxygen consume it and produce hydrogen sulfide. That smells like rotten eggs, which is not a good smell. Because of the railway, the Great Salt Lake is essentially 2 separate ecosystems, to the point that a 2016 study comparing the microbial communities in the lake found much greater diversity of species in the less salty region south of the railway. Now, it's kind of a fun superlative to be one of the saltiest bodies of water on Earth, but what we see today is not a sign of a healthy ecosystem for the plants and animals that would have lived in Lake Bonneville. What was once a giant freshwater habitat has become one of the saltiest places on Earth where only highly specialized microscopic organisms can live. And in a way, that brings us full circle. There's a fundamental principle in ecology that the health of an ecosystem can be measured through the diversity and abundance of the species within it. Essentially, the more diverse an ecosystem is, the healthier it tends to be. And that is known as the Patrick principle, named after, you guessed it, the same Ruth Patrick who first studied diatoms in Utah. The Great Salt Lake has seen some huge changes and continues to be a superlative in several ways. But we wouldn't know about all of that big stuff without the help of our tiniest friends, the diatoms. So don't forget to say thanks as you accidentally swallow a mouthful of them next time you go swimming in a lake or the ocean.